Live now on YouTube. All right, welcome back. We are Game 3001. That's Artificial Intelligence for Games in the winter 2022 semester at George Brown, and it's week 6, part 2 of our broadcast and recording. So last day we kind of talked about was division schemes, mostly. We talked about 3 different ones: tile-based graphs, points of visibility, and a navigation mesh, which I did a little kind of demo on with Unity. You guys like that, I think. This week we also discussed what the goals for the lab are going to be for today, and this is the goal right now. Let's kind of go all the way to the bottom here. We're going to make our tiles smart by creating neighbor references for each tile, and then we're going to use a right winding order. And right winding order is similar to what we do in on the web for the box model. We go top, right, bottom, left, and that's the winding order that we're going to use. We're going to set references to each tile, for inside of the grid. Okay. One thing to note is edge tiles will have neighbors that are null or null pointer. We're also going to be talking about these two heuristic functions, Euclidean Distance and Manhattan Distance. We're going to update IMGUI to enable heuristic selection, like we said. We also have to keep in mind when we're doing the distance functions that distance is equal to the tile cost plus the heuristic estimate, and the tile cost itself is going to be negligible right now because all of our tiles are going to be the same. Okay, so that's one thing to note. Or actually, it's not negligible. It's more like we can, kind of strike it out because we don't care about it. All right, we're going to make this dynamic so when the target moves, each tile updates the cost that's displayed. Okay, so that's the goal of today. Also note that there is a lab report that has been uploaded to Blackboard for you to fill out. So please make sure that it's an individual assignment. You fill out the lab report when you're doing this thing as we go. Okay, a couple of other things. I've also included a tool for you up inside of our course shell that's up on Blackboard. If I look up online, you can see that there is a grid system Excel sheet that I put up today. And this can help us kind of plan our grid. A lot of times, actually, I use this kind of thing when it comes to, hey, how is my screen supposed to look? And this is for your assignment too. I think it's great to start thinking about if I'm going to put things like, some kind of border or something like that, then how should the pathfinding work and how does the pathfinding work? Is what you expect the same as the outcome? I think these are good things. And we need to have some kind of expectation, right? And then what we do is we test our code to make sure that the expected result is the exact same as the actual result. Okay, those two things, because we're going to have sometimes a difference in between the two things. Hopefully not. Hopefully the expected result and the actual result are the exact same, right? But that's not always the case. And we'll talk about issues around that altogether. All right, so that's what we're going to start doing. And we're going to use this to help us as a tool. One thing I want to do now as we start is I'm going to bring up our project, right? So again, I'm just going to kill this one and bring up our project from last week. So under desktop, we had GBC and Game 3001, and we have our section 400, that's you guys. And we're using lab 4. So we're going to continue with lab 4 from last week. So please pull up your lab 4 that you were using last week. Okay, that's the one we're going to continue with this week. Okay, so it's a continuation of last week. Remember that we also, Alex had put up a lab 4 starter last week. So just in case, for whatever reason, you didn't attend last week and you wanted to complete lab 4, I think it's worthwhile to go back to last week, go through it, and you still have time to submit it before the end of the week, before Sunday when the lab is due. And remember that this lab is worth 8% of your final grade. Okay, so missing one of these 2 lab parts would be very bad. All right, so that's great. Let's take a look at this and start going. So I'm going to bring up the lab. And let's take a look at what we did last week and how it continues into this week. All right, I'm just going to close actually, we can leave some of this up. I'm just going to run it and just see. We always want to try and start back where we came from last week and kind of, make sure that we're all on the same page in terms of what we did. So again, here is our lab. I'm going to pull up IMGUI, and you can see that on the IMGUI window, I can toggle the grid on and off. But immediately what I noticed today when I was doing the lab, that what we did was I added a floating point number, and the floating point number, this number right here, right, is incorrect. This should be an integer, right? That's what should happen here. So we're going to fix this problem in IMGUI later on. Okay, that's one thing we messed up on last week. No one said anything, but I kept it as a floating grid, floating point grid, floating point numbers, but what we want is the exact grid location, which is actually not what we're showing here. Okay, so that's something we missed last week. We're going to fix that this week. All right, so let's get to it. I'm going to start off with, let's kill all of these things up here just to start off. We'll always like to start off on a fresh slate, if you will. Just close all tabs. And let's do it. Let's start off with the first thing, which is I want to add, and I'm going to follow Alex's little structure like we always do. So the first thing is we're going to add in a heuristic.h to the enumeration filter from the SRC folder. And right now it's been there the whole time. So we're going to go into enums. We're going to add a new or existing item, the existing item. And we're going to point to the right spot, which is inside of the lab4 SRC folder. There's going to be a heuristic.h file. And we're going to add that in as an existing file into our enumerations. So what does that look like? If I go to add it, you can see that heuristic.h includes a couple of enumerations. One of them is Manhattan distance and Euclidean distance. This is just a friendly name for 0 or 1, depending on how we're doing this, okay? We could have additional heuristics. We can have diagonal distance. We can have the null heuristic. There's a bunch of other heuristics we can also go into here and add them in. And we'll be talking about other heuristic functions coming up this week or the next week when we're hitting our final week of the first half of semester. So that's what we're going to be talking about this week. But for now, all we know about is Manhattan distance and Euclidean distance, those two. All right, so let's put this up on GitHub. Again, for the last course, the last class I used Gitkraken, but for you guys, I think we use GitHub Desktop. So we're gonna do the same thing here. And I'm just gonna point to the right repository. So that's you guys, section 400. And we only changed a couple of things. I'm going to say added heuristic.h to the project. That's what we did. It was always there, but we never really added it. And we're just going to push that up to GitHub. There we go. Awesome. Let's minimize that and move on. So that's the first thing we did. And I'm just following what we see here on Alex's kind of structure. And you can see that we're going to go forward. In the place scene, this is what he asked us to do next. We're going to add a couple of things. We're going to ask the heuristic to the place scene and set it to Manhattan distance. Okay, so this is the next thing we're going to do. So again, in the place scene.h, let's go to the place scene.h here. So again, we're going to bring up place scene.h and under scenes, place scene.h. Well, actually, I like to do it the other way around, scene.cpp and then .h, so it goes on the other side. There's .h. And I want to use the heuristic. I want to add in that heuristic little enumeration there. So again, include heuristic.h. Make sure you spell it right, okay, or it finds it for you. And down at the bottom here, what we have right now is some pathfinding objects and functions, grid, and it's the grid enabled, and a bunch of other stuff. I want to add in a little heuristic tracking, which is we're going to use the heuristic enumeration, and we're going to say that we want to keep track of the current heuristic. Again, remember, heuristic is a fancy word for distance estimate, right? It's our distance estimation function. That's what we're going to do. And it's really an evaluation function where we're going to kind of figure out what's the possible distance or the estimated distance between our start node and the end node. Okay, that's what that is. What I want to do here is I want to also have a new function that I'm going to put in called compute tile costs. And compute tile costs, what it's going to do is it's going to calculate the tile costs. This is going to make our tiles quote unquote smart. It's going to compute the tile costs from each tile to the goal tile. That's what this is going to do. Okay. So those are the two things we added. We added the heuristic tracker, which basically tracks which heuristic is active right now, the heuristic function, as well as I'm going to compute tile costs. I had to include heuristic.h at the top. Okay, let's add the compute tile cost stub inside of the placing.cpp by going here and then generating the implementation. Excellent. This gives me an empty function that I can use to fill in later. Okay. Are you with me? Check mark if you're with me, X if you're behind. Should be with me at this point. Going slow. Some of you are. I've got 5 out of 14 of you. Let's see if some other ones are with me. Okay, 7. Guys, I need you to follow along, or if you don't, and this is for everyone, you know, it's just going to become more difficult to keep up. All right, so this is great. We have the stub ready to go, and what I want to go to next is the start method. I want to go to my start method, so down here. And when we go there, we want to start thinking about what we're going to do. So one thing to note is I have my target at 1511. And again, if I was going to use my little grid helper, at 15 and 11, that is when my target is. So I can say that that is my goal, right? This is the little Excel sheet that I gave you guys that's on Blackboard. And we also know that the spaceship is, or which is the start, is at 1 and 3. Again, if I look at column 1 and column 3, I can see that this is the spaceship or the start. Start, goal. And that's a way of tracking. If I made some kind of obstacle in the middle, you can see what the shortest path would be. Excellent. Okay, good. So that's what I want to do. But I want to set my start and my goal here in my placing.cpp. So my start and goal. And the way to do that is to change the status, set the tile status of my start tile and my target tile to what there should be. So for my target tile, let's set the tile status. I want to say that m underscore get tile. And I want to get the tile where? At 15 and 11. So 15 and 11. And what I want to do is I want to set the tile status to goal. So I'm saying, hey, go to tile, the tile that's inside of 15 and 11. Okay, so this is accessing tile space or grid space, and set the tile cost to, or the tile status to goal. I want to do the same thing for the spaceship, where the spaceship is. I want to set the tile at 1 and 3, where the spaceship is, to the start. And yeah, this is pretty good. And while we're at it, by the way, let's update our IMGUI, because we're going to fix our IMGUI function by going down to our IMGUI function down here. Our GUI function is incorrect. Remember I said that we're using like slider a float instead of an integer. Let's change the static value of our spaceship properties from a static float to a static integer. Same thing with our target. It's going to create an error because you can't have an integer converted to a float this way. And we need to change this from an IMGUI slider float to an IMGUI slider int. an int. And when we do an int, we can go from 0 to the column number. That makes more sense. Again, I'm going to do the same thing here. It's going to be a slider int 2, and it's going to go from 0 to the column number. So that's going to fix our bug. That's a bug that we had in our code from last week. Okay, and let's run this. So the only thing I've changed here in our IMGUI function is from float, I went to int, and from slider float 2, I went to slider int 2. Okay, this is to fix my bug. And then when I run it, which you see a couple of changes. It feels like building. When I pull up the grid, right, you can see that, well, we can't see anything, can we? This is better, right? So when we move our grid around, this is good. And here is the start, right? Our start is right here, and down in here, right? We can see that this was our goal. It'd be nice, though, if the start and the goal is marked off not just as S and G, which is nice, but also the whole tile is marked off so we can see what the start and goal is. And Alex has really had a really nice idea. He said, listen, why don't we use the Util class? So let's go into our Util class. And under util.h, we have a function that is draw filled rect, right? Draw filled rect. Let's go there. And he made some changes to the function to make it usable. There's a bit of a bug here too, by the way, that we found. So he came up with this. And in our util.cpp, under the draw filled rect, we want to make this the following changes. Again, we'll update this on our framework in the future. But for now, we want to change this, right? So again, if you can see that we have these surfaces, let's get rid of these surface references. So surface references, goodbye. And we do want to set render draw color, but what we don't want is to SDL fill rect. We want the SDL render fill rect. It's one function. So many functions in SDL, it's amazing. And instead of passing in the surface, we just want to pass a reference to the renderer and the rectangle we want to draw. So this can change to the renderer and a reference to the rectangle. And that will allow us to draw a filled rect, and we can remove this part right here. And that should fix our function. That's the only thing we have to change in the function. So now the function looks like this, right? And what this will allow us to do is draw a filled rect where the start and goal tile is. Okay, and this is the updated function. I'm going to copy paste this into your chat. So I got to move on. So where do I change this? Well, I want to change my tile class, right? So my tile class from last week, I want to go into game objects. I want to go into my tile.cpp, and where the tile draws right in here, right? What we want to do in here is change the tile class to basically draw different things based on what we're looking at. So if my status of my tile, we're going to switch on status. If my status is, and we can use a switch case here instead. Let's use a switch case. So we can switch on status, right? And we can say that case the status is start, then do something. And it'd be nice if we actually do the right things, start. And case the status is goal, then do something else. But by default, we want you to do something else. So what is the default? This one. This is your default case, right? So here's your default case. By default, we want you to draw this, right? This position, which is just a rectangle, right? However, if it's the start or the goal tile, we want you to draw a filled rect. Let's do that. So we'll say util, and we want you to draw filled rect, and the filled rect is going to use the get transform dot position of the tile, and we want to use get width and height, just like before. And the only thing we want to change is the color, which is a GLM Vec4. And the color for the first one is going to be 0.5F, 1.0F, 0.5F, and 1.0F. And this is kind of a greenish color, like a lime green. And then what we want to do is we want to do the same thing, right? But we want to change the color for the goal tile. Let's change the color for the goal tile here. And we'll change this color. Instead of it being a green color, we'll make it more of a red color. Okay? That's the goal tile. Is this active? I don't know why that's even showing there. All right, does that make sense? So that is going to be our draw function inside of our tile. And I'm using a switch case to do that because I could use if else, but this is just a little bit cleaner. And I'm going to take this draw function, I'm going to copy that and put it into your chat. I'm also going to check out YouTube to make sure there's no questions. Sam says he's here and he's got a thumbs up. Awesome, Sam. Thank you. All right, so that makes sense. So then let's see what effect this has when we're drawing our tiles. So again, we're going to go up to our code. We're going to run it. And if everything goes well, when we put it into toggle grid, we're going to see different colors. Except when we move our object around, we don't see this thing moving with it. We want this thing to move along with it, right? That's what we want. And by the way, if I wanted to see my objects in here, right, what I could do, what if I wanted to set the value here instead of 100%, if I set the value of the color to 50%, how could I do that? Let's say if I did something like that. And if I ran it, let's see if that alpha transparency works in the field rect, right? So again, all that does is it changes it so that it should be somewhat transparent. And it's tough. It's tough to make that transparency work, see? So the transparency, although we were using a fully transparent color or a fully opaque color here, the value here doesn't seem to make a difference for our draw filled rec. Again, this is something that we need to work on when it comes to drawing tools for our little framework. Okay, so that is what it does, but it'd be nice if it followed us around, right? And of course, the way to do that would be if the start and goal follow the ship and the target around when we move stuff. And we can do that inside the placeScene.cpp in the same spot. So here's where we updated our slider int2s. We said these are incorrect. And what we want to do here is we want to say that the status, we want to change the status of the tile that our ship was in, right? We want to change the status of the tile to something else. So again, we want to teleport down to this place here, which is the IAmGUI area. This is the GUI function. Okay, so please make sure you do that because that's where we're going to make our changes. Okay. So what does that look like? Well, we're going to peek inside of the tile that's there. So we're going to say, okay, for the spaceship, let us peek inside that tile. What's inside that tile? We're going to use the m_p spaceship, and we're going to use the get grid position. We want the grid position, right? And what I want to do is I want to set the tile status of the tile. This gets the tile at this grid position. That's what this is saying. And set the tile status of this tile to unvisited. And where unvisited is like the equal sign, okay? And actually, we want to do this for both the spaceship and the target. So when we move one of those two things, set this back to unvisited. That's what we want to do, okay? And we just change this value from spaceship to target. And let's check this out and see what this does just by adding this one line in the IAmGUI function, right? When at first it'll show up, and as soon as we move it, it'll switch off. Let's try this. So again, it shows up, and when I move it, it switches off. right? Goes back to unvisited. And to put it back on, it's the exact same thing, but a different status. Instead of it being the tile status is unvisited, the tile status is for the start position, the start. And that's for the spaceship. And it's exactly the same here. Instead of unvisited, when we move our target, then we want that new place to be the goal. Right? So that's the changes. Unvisited, we just kind of mark the tile as unvisited. We mark the tile as start when we move it. We mark the tile as unvisited for the target when we move it, and we mark the tile as a goal when we move it to the new location. The stuff in between is that localization stuff we talked about in lecture, right? We said that we can use localization and quantization to convert from, actually it's quantization and localization, to convert from world to grid space and from grid to world space, right? That's what we're doing here. So notice what we're doing here from before is we're saying, I want to have the position of my ship be snapped to grid, right? In order for me to do that, I need to convert it from grid space back to world space. I want to convert my position of my ship to grid space. So I want to get a grid space to world space conversion, and that's what we did last week, okay? Okay, and then we record the new position on the ship. The ship always keeps track of its new position. Okay, let's try that again. And if we go back to run it, let's run this again. We should see now that when we move our ship and our target around, that so too does the start and goal coloring. Okay, that's what happens there. So it's looking pretty neat there. All right, let's put this up on GitHub. So again, I'm going to use GitHub Desktop. And I'm going to say added build rect, right, is what it is, to highlight start and goal tiles. And then commit to main and push it. Okay, status check for you guys. Are you with me? Do you have the same thing right now? Can you move your ship and target around? And can you see the start and goal tiles? Is that possible? How are we feeling there? Okay, I got some people that are with me, and I got some people that are not. We're not showing that they are. Not a lot though. I got 7 out of 15 guys, like less than half. I'd like to get that number up, so hopefully you guys can again respond and be participatory. All right, so this is good. So this is the first start. And again, if we look at what Alex has asked us to do, we've done some of this part right now at the bottom. I kind of did it at the beginning because I'm like, hey, well, I'm moving my ship around, you know, as an example, and I want to set the goal and the start positions in IMGUI. We haven't called the compute tiles yet, or we haven't, well, we have it there. We have it there, but we haven't called this, and we haven't made our changes to our build grid in order for me to compute the neighbor costs. So that's the next thing I want to do. I want to start thinking about, and the goal really is for today, like I said, if I look at the goals for today, it's really to display the distance to the target for each tile. That's really the goal, one of the main goals for today. Make them smart, get them neighbor references. I want to do this part first. I want to get the neighbor references going for all the tiles. What neighbor references mean are, and we have some edge cases here. We have all of these cases. I'm just going to kind of highlight those areas. So all of these areas on our grid are special cases. And the reason why they're special cases, I'm just going to highlight those with a light color like this, is that they have 3 or fewer references. So example, in the case of our start tile, it has a top, right? It has a right, it has a bottom, and it has a left neighbor. And so too does our goal, right? Okay, so we have all those neighbors, right? We're going to use the neighbor tiles to calculate the total cost of the total trip length from the start to the goal. That's what we're going to do. Okay, start to goal. So the idea here is I want to map each of the neighbors for every tile in the grid to get neighbor references going. Okay. Last day, all we did was we just laid out the tile. And that's what our division scheme. We're using a tile-based graph is what we're doing here, right? And we're using a vector, which is a vector of tile pointers. That's what we're doing, okay? And we're talking about the STL vector, which is like a managed array. That's what it is. So what about these things, these pieces here, these areas here? These have less than 4 tiles. For example, the corner tiles, they might only have 2. So the right and the bottom. What about this one? This one is null pointer. It's in the dead area outside of my map, right? And the same thing goes with this one. This is the dead area outside of my map. So there is no left or top pointer. These things are null pointer, right? One other question I had today was, what about the corner tiles? Are we doing anything with these tiles right here? This one, this one, this one, and this one. And the answer is, remember, we said that we will not be using the corner tiles for traversal. We're not going to use those. We're not even going to make references, right? All we're going to do is make references to the 4 tiles, not 8 of them, which will also add a constraint from your assignment 2, so you cannot move diagonally. You can only move, in one of these 4 directions. So that's what we want to do here. So where do we make these changes? Well, we're going to do that inside of the build grid method for now. However, I'd like to mention a couple of things. Let's jump to that method, build grid, right? I'd like to mention a couple of things about this. Using the idea of the single responsibility principle, adding an additional thing in here, but for the build grid method to do, you could say that you might be able to argue that it's really just building the grid, and part of building the grid is making neighbor references. Or you could also say that, building neighbor references is a separate function that should have its own function itself. But what we're doing here last week is what we said is, lay out a grid of tiles. That's what we're going to do. And what we did was we used a double for loop to do this. Well, I'd like to use the same double for loop we used before in order for it to do the same thing. So I'm going to grab these 2 things, this whole thing, and copy paste in here. So copy paste. And what I want to do is I want to delete all of this right now. So that's the first thing I want to do here. Because I want to still loop through each row and column just like we did before. But this time, what we're going to set up is we're going to set up the neighbor references for each tile in the grid. Okay, that's what we're going to do. And what this is, when we think about it, right, is each tile is kind of a node in our graph, right? So when we think about tiles equal to nodes in our graph. And when we think about what nodes are, some people asked this morning or earlier today, they were like, what's a node? Well, a node is just a point inside of our map, right? So this is a node, this is a node. All the tiles are nodes. And what we want to do is we want to make connections from one node to the other node. Now, instead of making connections and making a very dense map, and so that each node has 8 connections with 300 nodes, that's 300 times 8. Okay, 300 times 8, which is 2,400 connections. That's what we would have for a very small map. If I only have 4, that's half of those. So it's still, again, around 1,200 connections or less, okay, which is pretty cool. And what I mean by connections are, if we were to draw these, let's just use an annotation to do this. And I'll use arrows like we did last day, right? If we draw these, I have a connection from each tile, to the other tiles. These are the connections, right? And those connections are the only places that we can traverse from the start tile to the, to the top, right, bottom, or left, right? Those are the connections. So that's why we're only going to make 4 of them. Otherwise, we'd have 8 of them for each tile. That's a lot of connections for each node, right? And each node would have the same amount of connections. So that's 8 times the number of nodes or whatever. That's why we cut it in half. Okay. And also to make it more interesting, when we can only go right, to one of these 4 directions, it makes traversal a little bit more challenging. We'll talk about that in a bit. All right, I'm trying to go slow here to give you a chance to A, catch up, and B, understand, hopefully, a little bit more than what we're doing. All right, so that's what we want to do. And what I want to start off with is, let's get a reference to the current tile that we're in. So starting off using the row and column, the way we're going to march around in the grid is we're going to start off like this. We're going to start off at row 0, and we're going to start off at column 0. We're going to start here, and we're going to go march across. That's how we're going to iterate with the for loop until we get to the end. And then we're going to go and increment the outer for loop to go here. So the outer for loop does this, right? The inner for loop does this. And what we're going to get at the end is a spot inside the grid. That's what we're doing here. That's why we have these 2 for loops. So what I want to do here, instead of making a brand new tile, I want to say that m_get tile. Let's get a tile at the column and row. So look at that column and row. We just made a grid of tiles, right? Look at the column and row in there, and then set up the neighbor. Now, one person had asked earlier as well, why don't we just do it in one for loop? Could we? Could we do it in one for loop? Can we do everything, set up all the neighbor references in one for loop? Is that possible? What do you think? Ethan says, not all the tiles are made already. Correct. Stanislav says, we don't have all tiles created. Correct. How can I make neighbor references when all the tiles, the grid hasn't been created? So first we need to create the grid, and then we need to make neighbor references. So theoretically, we could make this a separate function after this one that basically says, okay, make a grid of tiles. Okay, cool. Now make neighbor references. 2 different things, 2 different actions. Okay. Again, to keep it simple, we're just keeping it into one function. So first we want to look at the following things. We want to look at the top, right? We want to look at the right. We want to look at the bottom. And we want to look at the leftmost tiles. Okay, so bottommost tiles. What are they, right? The bottommost neighbor, the rightmost neighbor, right? We'll say that one. Okay, that's what we want to do. Let's change tile to neighbor. The topmost neighbor. That's the order we want to wind in, okay? And the reason why we've chosen this order, we need to choose some kind of order to align the neighbors, right? And remember, we're actually using the same alignment as the neighbor tiles we had in the enumerations up here. Neighbor tile. Neighbor tile is exactly that. Top, right, bottom, and left. This exact way is what we're going to do. Top, right, bottom, and left in terms of the way we're winding. When I say right winding, it really means that. It means that I'm going towards the right every single time. Again, you don't have to do it this way. I'm doing it this way because that was natural to me. So in other words, I'm going to start at the top. I'm going to go from here to here to here to here and then to here again. That's the way it's going to go, starting at the top, right? And again, this is aligned with the box model from web development. If you do web development, it does the exact same thing. Okay? And that's why I'm using this, because it's familiar to some. All right, so that is the tile, the neighbor tiles. And this is the topmost, rightmost, bottommost, and leftmost. That's right winding order. All right, so then let's think about some edge cases. Here's some edge cases. What if the row that we're looking at is at the top, topmost row? What happens there? Well, what is our neighbor, the topmost neighbor, if we're in the topmost row? So that means if we're here, okay, if we're up here, all these ones, all these tiles that we're looking at, if we're all these tiles, let's look at those tiles right now. What happens if we're here? What's the topmost neighbor? Well, it's the gutter, right? That means the topmost neighbor has to be null pointer. That's what these are. For all topmost tiles, then all the neighbors above that tile are just the gutter, which is null pointer. Makes sense? It's outside of the map. So for all rows that are, if the row count is equal to 0, that first row, if you will, or the 0th row, we can say that the tile, and we can set the neighbor tile, we set this up in the tile class, and we're looking at the top tile, right, is null pointer. That's what we're going to say for that one. Okay, what about other edge cases? Let's just do the edge cases first, just to be clear about this. How about the rightmost tiles down here, the rightmost tiles? So for these tiles here, right, we got to be at the rightmost column, right? So that means if my column is equal to config column number, the maximum column, -1, because why? Column number is the 20 minus 1 is 19, right? The 19th column, right? If we're there at the 19th column, then guess what? The tile, we'll set this up here like this, right tile, the right tile is null pointer. That's also another case. Okay, how about the bottommost row? So the bottommost row is this one here, bottommost neighbor. And what about this one? Well, that means that all of these are them. And if I'm in the bottommost row, I'm here, which means that I'm in the config row number -1, right? So again, it's like same as this. Copy paste. And instead of column number, we're row number. If my config row number, and then we're looking at the row, if my row is at the config row number -1, then my bottom tile, right, is null pointer. Does that make sense? We're just setting up all the null pointer cases. These are all the cases for null pointer. By the way, you could be in a corner where 2 of these would be used at the same time. Leftmost neighbor. How about that one? That's this one. That's from here to here, right? And that means when my column is 0, my column is 0, right? So we said row is 0. Well, this would just be column is 0. We're going to grab this one, and we're going to say when my column is 0, so that we're at the left side, right? Then the left tile is null pointer. And we're going to use else's, but there's other ways, obviously, to write this. So what about if we're not on the topmost, but I want to still get my topmost neighbor, but I'm not in that edge case, right? I'm not in those edge cases. So I want to do this part now, the else's. And I want you guys to help me out, okay? We'll do one together. So else, so I want to find my top neighbor, but I'm not here. I'm not here. Let's suppose I'm here at 1, 3. Okay, let's suppose I'm right here. My top neighbor then would be 1, 2. Same column, a row minus. Row -1. Same column, row -1. Okay, that's what I want. So that means that if I took the same thing to start, we would say that for the top tile for every other tile, then what we want to do is we want a m_get tile, the tile that is at the same column, right? The same column with a row that's -1. Right? Does that make sense? So again, I'm here and I want to know this one. We're in the same column because I want to go from here to here, right? But the row goes from 3 to 2. That is in my top tile, a tile above me. That's what we're doing here. All right. We're saying that this is the case. Okay, cool. I like this. All right. So now help me out. How do I do the right one? This is for you to answer. All right. So what do I do with the right tile? I'm just going to copy this in here because we're caring about the right tile. What about in the case where we're not here, right? we're actually here, and we want to look at the right tile. What would be the combination here? So, okay, Tarif says column +1. Stanislas says right tile, and then column +1 and row. Okay, let's see if that makes sense. Okay, right tile is column +1, but the same row. That makes sense to me. So column +1, and then the same row. Okay, that's what we're doing here. So do you see what we're doing? Let's figure out the last ones. Okay, the last two. So again, I'm just going to copy paste here. Make sure that this says bottom tile. And again, what we want to do is we want to say that this is the same column, right? Same column, but row +1. So we're going to go down one, same column, but row +1, right? For the bottom tile, similar to this one, but opposite. That means that if this will probably be the same, but instead of positive, it'll be negative. Let's see if that's true. So I grab this one for the right tile, go down here and paste it in, and let's figure this out. So the same row, but column to the left. So this would be -1. Make sense? And that's how we're going to set up all of our neighbors' references, by using build grid. Does this make sense? This idea of neighbor mapping. We need this in order for us to get the tile cost of the next neighbor when it comes to setting up our path, our shortest path next week. That's what's coming, right? That's why we're doing this stuff. All right, let's go into our another part, and let's see what happens. I'm going to put a breakpoint now. After I've coded that, I'm going to put a breakpoint after build grid on around line 64. So I want to see what the grid looks like. So let's run it. It's going to immediately stop. And when it does, I want to look at the breakpoint, right? So I want to look here. I can see that we have a grid of tiles in here, and we can see that we have all the tiles. I can look at the tile this way. I can go into the neighbors, and I can inspect the neighbors, and I can see that the 0th neighbor is null, and the 3rd neighbor is null. So remember, top, right, bottom, left. So top neighbor is null, makes sense because that's the 0th tile, and the left neighbor is null, right? Just to give you a sense of it again, we're right here. Top is null, left is null, to the right is something, and to the bottom is something. Take a look. To the right is something, there's an actual reference, and to the bottom there's something, there's an actual reference. And that's how we look at the references, but we can actually see the pointer address right here. These are the pointer addresses, right here. Make sense? We can also, instead of looking here in our locals, right, or autos and locals does the same thing. We can look at those things. Just lays it out in a different way. I can also go back to my placing.h, even when we're in a breakpoint, right? And I can hover over my m_p grid, and you can do it this way, where you can show it here. Okay? So m_p grid. And I can also pin it. I can pin my grid if I want to watch it, and I can go into any one of these tiles. Let's go to the bottom right. The bottom right would be number 299. So we can kind of just rush to that point. So I'm just going to scroll down. You can see that these are all the tiles in my grid, and every one of them have a pointer reference, right? And this is the important part of seeing all the pointer references and checking. Here's the bottom pointer reference, X0X091CBC80, this one. And if I look down, I can look at the neighbors, and you can see that my top neighbor, that's the one that's just above me, right, in the grid, and there's the one that's to the right. So again, look at this. So it's top, right, bottom, left, bottom, left. Is this right? Does this look right to you? Top and right are okay, but bottom and left are not. Something seems off there. How do I know it's off, guys? Because look at the references, right? Top reference, let's take a look at the grid, okay? We're looking at the exact, this one. So top is okay, right is not good, bottom is not good, left is okay. So I'm going to have 0 and 4 are okay, that's what it should be, but 1 and 3 are bad, right? Because that's what we're looking. We're looking at the 299th tile right here. Let's take a look. Let's look at that again, right? So we don't have to look at it here because this can be cumbersome. Let's look inside of here, grid, and we can scroll down all the way to 299, and we can look here inside of our neighbors and see that this is incorrect. It should be top is okay, right is null, bottom is okay, is null. This is good, and left is okay. So we've mixed up some stuff. Let's make sure we're good inside of our references and see what the problem is. Do you see that problem? Let's take a look and see if we're right, because that has to be right before we move on. So again, going back to here, and I'm going to scroll down till we get our neighbor references, and let's see what we've done wrong. So top, right, bottom, and left, those are good. Oh, look at that. Man, what the heck? That's a copy-paste error. See, I was right. There's a problem. I swear I didn't do that on purpose. I swear. Okay? Let's see if we're right now, right? Because that was an issue. So let's just run it. And I wanted to show you this, the debugging that we can do, because again, what we want to do is we want to be able to debug our code. If something doesn't look right, you know, that would be a tough bug to find later on, right? So that's why I'm checking it now, right? So I'm going back here, going to neighbors, scrolling down, and now it looks like it should. The top and the left are good, but the bottom and the right are bad, which is what it should be. And I mean bad as in they're in the gutter. Right and bottom are in the gutter, top and left are okay. Now everything is okay. All of our references are good now. Let's stop. And let's get rid of this breakpoint because we did our testing. Cool. And let's put this up on GitHub because we know it works. So going back to here, we're going to say added neighbor references for each tile. Okay, commit to main and push. Okay, I'm doing another sanity check. Are you with me? And I'm going to ask to this, when I say are you with me, not just in code, but do you understand? Check mark if you're with me in code and you understand. I've got 5 out of 15. 6. It's not a lot of you guys. What about the other people that are here? What is the issue? This is the time to ask because we only have a short time together before, you know, this lab finishes. Again, remember this lab is worth 8% of your final grade and it ties into your assignment 2, right? So if you don't understand this, then assignment 2 will be perhaps challenging to understand how to use, right? How to do properly. All right, not too many. 7 again out of 15. It's almost half. Almost half, not quite. Okay, interesting, interesting. So that's what we did so far. And we're just following Alex's guide, right, as much as possible. We did, you know, we're starting to figure out the neighbor references, and we did the neighbor references first. So we just did, and the reason why I think neighbor references are more important than computing tile costs, because without neighbor references, we don't have any path. So that's what we did here. We did this part. All right, well, now that we have our neighbor references, it makes sense that we start filling out our, to compute our path, right? So I'm going to scroll down here where we have that empty stub, compute tile costs, and this is where I'm going to start putting it in. So I want you to think about what this is going to do. This is actually going to show our display the cost from each tile to the end goal, or the goal, if you will. So we need to set up some variables. One of them is a float that we're going to call the distance, because we need to know the distance function. And we're going to set this up at 0, 0. Okay? And we're also going to have, for Manhattan distance, we need the difference of x's, right? Or dx, which we're going to set up as 0. And we're also going to need the difference in y's, which we're also going to set up as 0. We're going to see where that comes into play in a second. Okay? I want to loop through, actually, let's do it this way. For each tile in the grid, this is kind of the pseudocode loop, okay? And we can put a comma there. And we're going to use a for each statement, which looks like this, the arranged for loop in C++, where I can change the collection to m_p grid and the element name to tile. So this is exactly what we're saying here. For each tile in the grid, right? Then what we want to do is we want to loop through, and we want to do a couple of things. We want to decide, depending on the heuristic that we're using, right? I want to calculate the distance. Calculate the distance from from each tile to the goal. That's what I want to do. Calculate the distance. Let's not use calculate. Let's say compute, which is better. Compute the distance from each tile to the goal tile. That's what we want to do. Okay. But we're going to need to use one of two heuristics. So it really depends on the current heuristics. Let's switch on the m_current heuristic. We haven't set that up yet. We're going to do that. What is the current heuristic? So there's two ways. We can use the first case, which is the Manhattan distance. That's one of the heuristics we can use. And we can use a second case, which is the Euclidean distance. I'm doing it in this order because that's the way we have our, this is the way we have our enumeration set up. And then once we figure out what the distance is going to be, we're going to calculate the distance depending on the heuristic here. Then we're going to add that, we're going to update the tile cost, right? Depending on the heuristic, the distance. So down at the bottom, inside the for loop, we're going to say for each tile, we're going to set the tile cost, right, to that distance, whatever that distance happens to be. Right now, the distance is 0 because we haven't made any changes here. And we also haven't set up the default heuristic. We didn't say that Manhattan is default or Euclidean is default. Before we continue, let's do that in the start method. So we're going to go into the start function, just one sec. And we're going to say that in the start function, somewhere in the start function, we should probably set the default heuristic to something. And I'm thinking about putting it right underneath the offset here. So we're going to say something like m_current heuristic. Let's set that up to Manhattan by default. Okay, that's what we're going to set. And so this way, at least when we go back to the compute, we're going to compute the tile costs, right? We're going to start with Manhattan. This is where it's going to go first, Manhattan by default, okay? So that's how we're doing it. All right, well, Manhattan might be a little bit more difficult to figure out, but Euclidean, right? That really computes the Euclidean distance, which is the as the crow flies, so straight line, for each tile. Okay, so how does that work? Well, that's easy. We can say distance, that's equal to, we can use our utility function, util distance, and we can pass in the grid positions of the tile and the target. Tile get grid position, and the target get grid position. And that is the Euclidean distance, right? We're using the distance formula. If you look at the utility function, go to definition, we're using the square root of x squared plus y squared. Okay, that's the distance between the first vector and the second vector, vector A and vector B. That's what that function is going to do, the Euclidean distance. But what about Manhattan distance? We don't know the formula for that offhand, but we do have the old PowerPoint, which is right here from last week. And the Manhattan distance says that the distance the heuristic is the absolute value of the difference of x's plus the absolute value of the difference of y's. And the way we're going to calculate the difference of x's is we're going to take the current tile, minus the goal tile, which is the target, for x's and y's. Remember what we're trying to calculate here. To compute the distance, right, the distance formula, which is h, right, is equal to the tile cost, which is g. Let me go back at the end, do that again. F, I'll be okay. This is g plus the heuristic, heuristic function, heuristic estimate, we'll say, which is h. Okay, that's the how you find the distance. F is equal to g plus h. This formula we saw when we're figuring out the heuristic, right? So F, the distance, we don't have a tile cost. Tile cost is 1 for everything, so we just remove this. We crossed it out, right? And all we care about is heuristic estimate. So distance is really just a heuristic estimate for us right now, for now. And so let's code that. So we're going to say something like, okay, we want to find the difference in x's. That is equal to the absolute value of tile get grid position dot x minus m underscore p target get grid position dot x. And that is the difference of x's. We can do the same thing for the distance of y's, right, or difference of y. So we're going to say dy then is the tile at grid position y and the target at grid position y, okay? And once we have this, then we can set up the formula, which is distance is equal to dx plus dy, which is exactly what we're showing here. Okay, distance is equal to dx, difference in x's, plus the difference in y's. And that's what we're doing here in Manhattan distance. And this is our first heuristic. Cool. We've done the compute tile cost function, and now we need to call it somewhere in order for it to kick in. Let's do it inside of the start method. Again, going back up to the start to test it. We're going to go at the bottom of the start because we want to set the default heuristic, set up the target location, set up the spaceship location, set up everything else. And then just before the IMGUI function, that should be last, we're going to call the function m underscore p compute, or m underscore compute tile costs. And my friends, if we did everything properly, we should see the tile costs in the grid. Let's try it out. So we're trying it out, and if I go toggle grid, then you should see the tile costs. And these tile costs are for Manhattan distance. This is okay, but we want to be able to toggle between Manhattan distance and Euclidean distance. Okay, and if yours doesn't look like this, well, then something went wrong. Also, I can move this, that's okay, but if I move this, I want the tile cost to be automatically updated. So some more things to do. All right, let's put this up first. So we'll say that we added tile cost, made all the tiles smart. So we'll say added tile costs for from each tile to the goal tile. That's what we did. Commit to main and push to origin. We did that part, but we still have some work to do. What I want to do now is update my IMGUI function, right? So that's one thing I want to do, the GUI function. Let's go there. Should be at the top. And what I want to do is let's set up some more information or more things we can do here. All right. So by the way, still love for debug properties. That's okay. The toggle grid is good. And we want to have a separator, but I want another separator. I want to set up another separator here. So between the two separators, I want to set up heuristic selection. And the way we're going to do that selection is we're going to use a radio button. So we're going to use a static integer radio, and that's going to be equal to the m underscore current heuristic, because the current heuristic is an enumeration between 0 and 1 right now. Cool. And then I want to set up my IMGUI. I'm going to say, hey, IMGUI, I want a new label that's going to say heuristic type. Okay, going to kind of show our heuristic type. We also want to say, hey, I'm GUI. I also want a radio button. The radio button is like basically a little button that you can press. And I want two choices, Manhattan. Okay, that's the first part of the radio button. I want to make a reference to the radio integer. And depending on if I chose this one, I want to take the value of Manhattan, which is in this case 0, and assign that to the radio integer. That's what I want to do. Okay, in the same line, okay, I want to put another radio button. Just going to copy paste this one. And I'm going to change this to Euclidean. And I'm going to say that I want to take the Euclidean value in my enumeration, that's 1, and I'm going to save that in the radio button. So that's going to be my switcher. I'm going to switch between Manhattan and Euclidean or back. That's what I want to do. Okay. Excellent. And then how do I actually do the switch? Well, it's going to be something that looks like this. Okay, check if my current heuristic, whatever it is not equal somehow to my radio, whatever we just changed. So I just changed the radio because I assigned it something different than what I had here. It was originally set to the heuristic, but now we've changed something. If they're not equal, that means something has changed. And what I want to do is I want to say that my current heuristic is equal to the radio. And now we have a bit of a problem. And it says, wait a minute, I don't understand. How we can't set this radio to the heuristic? Well, the problem is we're converting from an integer to an enumeration. And to do this properly, we need to statically cast the integer back. We're going to static cast the integer as a heuristic. And this converts the integer to a heuristic value. And once we've done that, so that means that if I have a 0 or a 1, it's going to switch the current heuristic to whatever that is. And then what I want to do is compute tile costs again. So this is going to recompute tile costs if the current heuristic is not the same. So check if current heuristic is not the same as the selection, right? That we made up here. If it's not the same, then switch it. That's what we're saying. And then recalculate. Okay. And that is your, I'm going to take this I'm GUI part right here, which is maybe from here to here, and copy that into the chat for you guys so we can move on. I also want to mention that I know Alex, what he did in his video is he went through and statically cast all of these, but you don't need to. It's only when you cast back. All right, so if I go from an integer to an enumeration, I need to statically cast. Otherwise, it does it implicitly. Okay, you don't need to do these ones. All right, pretty good. I'm pretty happy with this. Let's check it and see if it works. So again, we'll run it. And now if I move my, if I change my heuristic type from Manhattan to Euclidean, it recalculates. Let's check these. All right, let's check this thing out and see if it makes sense. So if I was going to be here, and I'm in Manhattan version, right? The Manhattan heuristic. It's hard to see here, but it's selected. If I go from here to here, how will I march using my top winding? So top, right, bottom, left. I have my top and my left the same. On my right and my bottom the same, and my right and my bottom show that the rightmost, which is what I'm going to go next, is 21. That seems the next thing to do. So I'm going to march to the right to 21. So again, top, right, bottom, left, you can see that 20 is next. And what this is going to do is going to march across, keep marching across, march, 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 all the way to here. And then when I get to here, it's clearly that the value is lower here than anywhere else. These are all the same values. You're going to get to this point where all these are the same, but this value is lower, and it's going to march down from there all the way till it gets to its goal. That's how Manhattan distance works. And to track that, let's track it on our grid. So let's just get rid of all this for a second. Just for demonstration purposes, we should understand what's happening. I'm just going to get rid of some of these things. And let's track the course of our, if we're going to try and calculate the shortest path. We're going to do this again next week, okay? But let's suppose I'm starting to count. So I'm going to count 1. This is what Manhattan distance, Euclidean distance does. No, sorry, it's Manhattan, I was right. So I'm going to count like this, and let's just make these colors a different color. So we'll use something like a green color for this, something like this green color. There we go. And we'll say that I want to count up until I get to about right here, right? Makes sense? So 1, 2, 3, 4, 5, 6, 7, 8 tiles. Notice that it intersects with this, with the start. I'm counting backwards, right? And then from here, I'm going to go to 9. So let's go here, make this 9. And we're going to count back. This is using Excel. I'm going to count back from these 2 tiles all the way back to my start. So again, you can see that there's 21 steps, or 22 steps really, to get to my goal from my start, right? Using Manhattan distance. That's what it does. It does this. Okay, cool. What does Euclidean distance do? Let's reset. We don't have a reset button right now, but let's reset and see what it does. So run it again. And if I start it off and I toggle the grid and I go to Euclidean, it goes, all right, so this is what it wants to do. 15.3, 15.7, 16.6, and 17. Can't touch the corners. The corners are not allowed. We can't traverse them because we're not allowing you to do that. So the next smallest one is 15.3. In fact, it's going to look exactly like Manhattan until it gets to a certain point. 15.3, 14.4, 13.6. It's going to march across until it comes to a point of equilibrium where both of those things are the exact same. And let's take a look when that happens. Take a look over here, right? So when it's diagonal, I'm using Euclidean distance. When it's diagonal right here, at this point right here, right? I come to this point. Notice that those two are both 10.6. So from here, right here, where do I want to go? Well, I'm going to use, I can't go diagonal. I'd like to go diagonal, but I can't. I want to go this way, right? Because I'm going to go do things in a right winding order, right? I'm going to go this way first, and then the next possible one is down, this way and down, this way and down, and keep going like this. That's what Euclidean distance will do in a stepped manner. Okay, let's see how this charts with our graph for a second. Let's go back to our graph, and let's see how this works for us. So again, Euclidean distance and Manhattan distance are the same for the first part in this case. They go, but the ones in the corners, if I was going to march back, this is 2. Let's copy this and put it here. So 2. And let's change the color to make it something else. Like, let's say, yellow. We're going to make it a yellow color. There we go, right? And then from here, it's going to go this way, and it's going to go up to this. So this is the next step. So from 2, it's going to go here, right? This will be 3. From here, it's going to go here. This will be 4, right? And from here, it's going to go here. This will be 5, right? And so on. Like in a step manner. That's what it's going to traverse like. And let's just get these numbers right. So this will be 6, 7, 8, 9, 10, 11, 12, 13, 14. That's what it does. But for the first part, up until here, it's the exact same. From here to here, instead of it being different, it's the exact same. We'll make this an orange color. So this is the difference. This is Euclidean. This is Manhattan. Okay? So notice that it's the exact same number of tiles, the same number of steps. It's 21 steps or 22 steps to get to the goal tile if we're using Manhattan. And it's the exact same number of steps if we're using Euclidean, the exact same path length. But the path itself is very different. This is Euclidean, and this is Manhattan. And you might say that, well, Euclidean is always better, but actually it depends. It really depends on a couple factors. And one factor is if there's some kind of wall in the way. Okay, that's the difference. And it really depends on the configuration of that wall, right? We're going to talk about this next day. But for now, what I want you to think about is this pattern. This pattern is the important piece. This is Manhattan. Okay, we're going to write Manhattan here so you can see it. And this is Euclidean down here. Okay? But the number of steps are the same. Okay? All right, so that's what this is. That's exactly what's going to happen here. You're going to see that in the corner here, right? It's going to come to a point where it's going to start making decisions, 10.6 and 10.6, and then it's going to go exactly like that. This way, this way, this way, this way. It's going to it's going to use a step manner of approaching the target until it gets to here. Okay, that's what's going to happen here. Cool. And we would like to, right? I would like to be able to, when I move the target, I want to recalculate on the fly. That's what I want to do, right? And so let's put this up on GitHub now, because the first thing we did was we added the ability in IMGUI to switch heuristics. So added heuristic selection in IMGUI. Right, so we did. Okay. Does this make sense to you? What we did here with this radio button, we allowed the user to switch the heuristic from one to the other, and then when we recomputed the tau costs. Okay, let's think about this then. If I want to move my target, then all I need to do when I move my target is, as soon as I move my target, recompute. Let's do that. So put this at the bottom, m_compute tau costs, right? Here's our compute tau cost down here, right? And compute tau costs is interesting because what this is going to do is when I move my goal around, my target around, then it's automatically going to be computing tau costs. Let's see if that works. So again, going back out to the code, let's try it and run it, test it. How does it look? I turn it on, and when I move, this is Manhattan distance. When I move my target around, you can see that there's like a diamond that forms around the target, right? It's kind of hard to see, but try it yourself. You'll see that there's a kind of a diamond of costs that happens, right? And as I move closer, you should be able to move it anywhere you want, right down or way over here as an example. And as they do that, all the costs recalculate. And the path changes, obviously, too. Again, for Manhattan, it's going to go like this. It's pretty much, and it's going to go this way, but not this way, because we've decided on a right winding, because those two values are the same, 20 and 20 from this particular position, right? It's not going to go here, and it's not going to go here, because those two positions are higher cost than these two. Okay, if I change to Euclidean, it's going to be the exact same, but it's going to come to the point where, look at this. At some point, it's going to start switching, and it switches right away. Look, you can draw a diagonal line right from here to here. And in this case, this is where Euclidean distance is going to be different. Let's remap this one now, and let's take a look at this. So this one, right, if I go down one, it's, instead of going to the right, which Manhattan would do this, right? But Euclidean would not. Euclidean would start low and then go to the right and start marching down like this right away. Same number of steps, but it would have a very different path. Okay, so here, or this way. Okay, cool. So that's what it does, and we can update it no matter where I move. This is an idea of computing tile costs on the fly. Each tile has costs, and the next step, which we're going to head up next week, is let's compute the shortest path between where we are and where we need to go. Okay, shortest path between here and the goal. And we're going to put some obstacles in the way next week to stop us to go directly there. We're going to see if it is able to find the path. And how about if it can't find the path, there should be a base case to terminate the path finding so it stops. Okay, that's what we're going to look at and see next week. All right, let's put this up on GitHub because we're basically allowed our cost to recalculate as we move the target. So enabled or recomputed, we'll say recomputed tile costs when target is moved. Was. Okay, push. And you can see we've made like several commits throughout the entire time. Let's check to see if we've met all of Alex's requirements. Let's see if we've done that. So again, we started off with the setup, we did that part. We added the heuristic, we did this part. We added the compute tile cost function, we did this part, stuff. And in the place scene, we added a start method and add a heuristic to set the Manhattan distance as the default, we did that. We added a call to the compute tile cost in the start function near the bottom, we did that. And we added the body of the compute tile cost, but we did that in a different order. We did references first, then we did the compute tile cost afterwards. And we also added, I'm GUI heuristic buttons after we did the compute tile cost. We did that. And when we moved the ship's position, we recomputed the tile costs. And we did this piece almost right at the beginning because it was a cool thing to add. So that way we can see what the start and the goal tiles are from the very beginning. And that's pretty cool. And that's Lab 4, Part 2. Okay. Again, I'd like to direct you back to the requirements for this lab, which is the lab report. For the lab report, guys, please, what I'd ask you to do is when you complete the lab, make sure that you highlight the portions of the lab that you've completed that you feel are 100% complete. And if you couldn't do something, mark that as something else. Let's say, for example, you couldn't make the heuristic buttons work. They worked with errors. Mark that one, and you'll only lose the marks in the areas that you state that you're not, making it work. Okay, and then when I go through the videos for you guys, you're going to see that the total computed weight of this lab is going to be 8%. This is the last part for sure. Okay, so what is left to do? All right, let's go back to our little PowerPoint slide deck and see what is left to do now. So way back up here before we end for the day. So again, we did neighbor references to tiles, pointers, we computed Euclidean distance, Manhattan distance, and we set up this stuff for pathfinding. All this stuff is set up for pathfinding for next day. So what's left? Next week, we're going to be talking about more heuristics, diagonal distance, and best first search, and other ones that I'm going to include. Right? We're also going to talk about A-star variance and hierarchical pathfinding. Okay, that's going to help us out. And then if you look here, we're also going to create different methods next week. Find shortest path, that's going to be a method. Display the path list. We're going to create a spawn object method that's going to spawn random obstacles to test pathfinding. That's what we're going to do next week. So this is a very interesting week next week. We're actually going to culminate our pathfinding module, and it'll end at week 7. After week 7, we're not going to be talking about pathfinding anymore. We're going to go into the next section, which is all around decision making. Okay, so that'll be after the mid-semester break when we return. So that is what's happening. So it's very exciting, the stuff that's coming up, and it's great because it'll give us an opportunity for us to really show. We've really covered it by the end. 2 methods for traversal. One of them, which is steering behaviors, right, where we can search out and find, kind of a way of moving from one tile to the other, right? And of course, the other part is using pathfinding. Of course, the best would be if we combine both, using steering behaviors and pathfinding to find the shortest path and the best way of moving from our autonomous agent from where they are to the player, which is what we want them to do in the second half when you're using decision making. Okay, any questions around today before we go? Because this is lab complete at this point. I know some of this is challenging, and I know some of you have indicated that inside of our lecture that, it's tough to understand all the little piece parts. It's true. it's tough to understand all the piece parts. But the thing for you to think about when it comes to this is, you know, the general idea. Even if you don't get every single piece of code, the examples are here, but you should go through all of these things and try and understand what they do. Remember the conversion we're using, like we said before, we're converting from different coordinate spaces or coordinate systems, right? Or coordinate frames. They're called different things, but they mean the same thing, right? We're converting from world space into grid space, right? Which is our tile of grids, our grid of tiles. We're converting from tile space or grid space back to world space, right? In order for us to position our objects properly or snap them to grid. Okay, and if you look at what those are, if I go to the lecture this week, we talked about quantization and localization. That's exactly what we're doing here. Okay, so world to grid space is quantization, and grid to world space is localization. And those two things are crucial or critical for us because we want to have a division scheme in order for us to represent our a way of traversing from the start node to the goal node. Okay, guys, that's it for me today. I'm going to stop recording if there's no other questions. Okay, I'm going to stop recording on YouTube. I'm just going to check YouTube if there's any questions there. Had some students saying column plus plus or row minus minus. So we can't use unary operations. Why? Why can't we use the unary operation? That's a good question. That's coming in from Alex, actually. He's watching this video too. What are your thoughts, guys? Why can't we do column plus plus or row minus minus when it comes to how we did it here? So let's go back up to this and let's take a look and see. He's talking about when we're calculating when we're calculating the neighbors, and we're doing that in build grid, right? So build grid. Why can't we use row plus plus here, right? Can't we? Here's something else. What is row plus plus? What does row plus plus do? Okay. Why can't we use that here? Yeah, we're going to mess things up, right? It's actually going to add 1 to the row, or row minus minus. That's also something. Even if I did minus minus row, look, we're already doing that here, guys. This is what's happening in our for loop. And it's, although we want to go forward, this makes no sense because it'll actually change something inline. We don't want to change anything here. We just want to get the current row and subtract 1 from it. So actually what we're doing this is in one blow. We could write this as like the new row is equal to row minus 1. Like we could write this differently because it's something like, you know, var new row is equal to row minus 1. And we pop in the new row in there, right? That is what we really want to do, right? I mean, var auto. Sorry, see what happens when I'm writing in C# and C++ at the same time? This idea is what we're doing, but we're doing it, instead of doing it like this in 2 lines, we're actually doing it in one line where we're saying, hey, let's take this, let's evaluate this expression, and when we evaluate this expression, we want to put the whatever the result is, we want to pop that into our neighbor tile, and so we don't have to do this extra line of code. Okay, that's what's happening. If I did plus plus row or row plus plus, hey man, if we did plus plus row or row plus plus, the problem with that is that you know, we're actually updating the parameter on the for loop. That would not be good. We don't want to touch this at all. Okay, so please don't do that. That's why it's not good. And Alex is very right about that. We cannot use, and why? Because of that. Okay. Any other questions or comments at all? Otherwise, that's it for me today, guys. And thank you so much, Alex, for actually watching the video at the same time. But otherwise, that's it. And we'll see you all next week. Again, oh, one more thing, a piece of admin that we want to hit as well that we didn't cover yet is remember that you cannot do assignment 2, which is due next Sunday at midnight, unless you sign up for groups for assignment 2 groups. If you haven't done this already, please do so ASAP. If you don't do this ASAP, bad things will happen to good people. And it means you won't be able to do it. You'll be like, wait, Tom, Alex, I can't submit this thing. And I will say, well, did you sign up for groups? And then you'll be like, oh yeah, we did it. That's bad. All right, and that's it. Guys, take care, and we'll talk soon. I'm going to stop recording now on YouTube.